Today we're going to talk about these two multiplexers and switches, and we'll take a look at the data sheets, we'll talk a little bit about what they were originally used for, and maybe even some suggestions on things you could use them for today, and we'll also put them up on the oscilloscope and see how well they perform. Let's get started. Let's start with this one. This is the MC14066B, and it's a quad analog switch quad multiplexer. And the interesting thing here is the analog part, and we'll see that when we put that up on the oscilloscope. But if we take a look at the pinout, you can see it's relatively straightforward. There's quad, so there's 4 of them. There's one input and one output for each, and then there's a control. And so the control will turn it on or off, and what it's turning on or off is the output on pin 1. So if we feed in a plus on the input and the switch is on, then we'll get a plus on the output. But we can also feed in analog signals. So this allows us to control up to 4 different inputs with independent outputs, both digital and analog. If we take a quick look at the block diagram, you'll see here's the output here on the right, and then we've got the input on pin 1, and then that control here on pin 3. And as you can see, all 4 of them are completely independent. So this would be essentially a digital switch that we can kind of control what the output is based on the control pin. Other than that, there's not a whole lot more to say about it. Here's a little bit of a logical diagram here, which is probably a little more confusing than it needs to be, and the circuit diagram down here. Let's go ahead and put this up on the breadboard, and we'll do a real simple example and see if we can get it to work. So here we have it up on the breadboard. We've got the chip, and then I've got my 2 switches. This first switch is the control, so this is turning the output on and off, and then the second is just determining whether it's a 5 volt or a ground that's being fed in on the input. So if I hold down the control, simulating I want it open, then the switch on the right will then change the control. And as you can see, it goes on and off. So nothing super exciting about that. But there's 4 of them on there, and each one of them is independent. And what we're going to do is we're going to feed in a signal on the input, and we'll see how well the output tracks. But because this is also analog, what we can do is we can feed in a sine wave or some type of an audio wave and then be able to turn this on and off. And in order to do that, I built up this little tiny circuit real quick. And all it is a couple of 10 nanofarad capacitors and a couple 1K resistors. So if I feed in my sine wave here, or my square wave here, I'll get a kind of sine wave out here on the right. Now it's not awesome, but I don't actually have a signal generator, so this is the closest that we're going to get. But we'll be able to also feed that sine wave in as an input and see it work from an analog standpoint as well. So it's bound to be kind of interesting. So what was this originally used for? Well, it could have been used for a lot of different things. It was probably used to control different analog outputs, or maybe even some signal outputs, just like what we saw here on the switch. So we can digitally control whether or not something is on and off. Now, today, maybe we could use this in order to control the output. And if we've got 4 of them and we've got 4 different switches and 4 different outputs, we could then control which ones are on and off. Now, in theory, this is not going to have any substantial losses on our sine wave coming in versus out, and we'll go ahead and check that on the oscilloscope. I've got everything hooked up on the oscilloscope. I've got my little driver board here that is cranked all the way down to around 63 hertz. I've got my breadboard here. I've got the yellow line, which is 63-ish hertz, hooked up to the yellow line of the oscilloscope. And then I've got the blue one hooked up to the output. I'm going to take my LED out so that it doesn't draw any current out of that. And then we'll go ahead and take a look as we ramp this up. Now, right now, we're obviously just running it in a digital mode. We've got a high and a low. So as you can see on the oscilloscope, it handles it just fine at 60 hertz. Wouldn't really anticipate it any other ways. It's pretty slow. I do just have the control input wired high, so it's always going to be on, and we'll mess around with that here in a little bit as well. Let's crank this up to 5 megahertz and see if it can handle that. Here we are at about 64.5 kilohertz, and you can see it handles it just fine. We don't have any lag whatsoever. Everything's just spot on. We can actually even raise that up and superimpose those over each other. And you can see it's just a real slight slope on the front of that, but nothing to be concerned about. Now we've got it at 5 megahertz, and you can see it's a little bit more of a triangle wave on the output. And if we kind of superimpose those, you can see that it does lag a little bit, but I'm not sure that would get picked up from a digital service or not. But anyway, let's crank it down just a little bit and see when that kind of squares back out again. So it looks like around 840 kilohertz. It looks pretty good. So I would say this one at 5 megahertz probably is not going to function very, very well. I changed this around just a little bit. I added a different input, so on the control, so it's no longer tied straight to high. Instead, it's on this red line or the pink line on the oscilloscope, and this is half of the frequency as our input signal. So as you can see, we've got the purple, which is going to be the on, and that's going to be the signal on, and then the yellow is going to be the actual input, and then blue is the output. I'm not sure why we've got a little bit of a shelf on that. I'm currently triggering off of the blue right there, but I don't think that has anything to do with it. And this is down at around 62 kilohertz. Let's go ahead and ramp this up a little bit and just kind of see how this operates as we get up into the couple megahertz range. All right, let's back it down a little bit. Here's 500-ish kilohertz. Let me change the triggering on this. Now it's triggering on the middle line or the pink line, which is going to be our control line. And then this is our input. And as you can see, here's the output. So as long as the input is high during the control is high, the signal tracks. And then when the control drops to nothing, this drops as well. We've got a little bit of a shelf in there. Still not sure even up at this level why that is. So it's at 592 kilohertz on the input. Let's crank this up to 5 megahertz. And we saw this didn't really function very well earlier. And yeah, here it's even worse. Definitely not good at that high frequency. Let's back it up back a little bit and see there's 1.4 megahertz and there's around 850. Here's 1.4 megahertz. And yeah, that output's a little bit weak on there. So now that we've seen how it handles digital signals, I thought I would swap this out and let's add that sine wave in and let's see how that performs and if we can see anything unique. So I've got this set up with this little circuit here generating kind of a little sawtooth wave. I don't have any good way of doing a sine wave, and this will work fine for our purposes. We're just looking for a little bit of a non-square wave, and so this is going to be just fine. Now the input to that is going to be our main frequency here, which is 578 hertz. And then I've got the green line, which is going to be our control input. And that's going to be coming in at around 60 hertz. And then the output on the bottom is the blue. So on the oscilloscope, the yellow is our control, which is telling it whether or not it's on and off. And then this square or little sawtooth wave in the middle, the pink, that's going to be our input into our control. And then the blue on the very bottom is going to be our output. So as you can see, that is actually tracking perfectly. In fact, if we go ahead and move this blue wave up and zoom in, we can see that that is staying in alignment perfect. So there's absolutely no loss or anything on that output. So that output and the input, when that goes high and turns it on and off, is just perfect. Now I can't really go a whole lot faster than this other than when I do so because of my sawtooth wave guy, you're going to lose the signal. But we can go ahead and zoom in a little bit just for fun and kind of see what it looks like. But as you can see right there, we kind of lose the signal. And here we go. This is about as fast as we can get it. But we lost a lot of the amplitude on that. And that's running at about 1.4 kilohertz. So anyway, I thought that was kind of neat. Just gives you an idea of how you can control that switch and then also be able to use that in order to control both an analog and a digital input. So we can even slow that way down. That'll get us a little bit closer to, that's not quite sine wave there either, but you can kind of see how it's moving along and it's clipping it just perfectly based on when the control is on and off. So anyway, I thought that was kind of a neat little chip to take a look at. And the second circuit we're going to look at is this quad 2-input multiplexer, and this is SN74LS158. Now this one's a little bit more complicated than the last one, but it kind of works similar. It just has a lot more kind of internal switches. So if we take a look at the logic diagram here, you'll see we've got 4, meaning the quad, and then we have 8 inputs. Now the 8 inputs are also going into these AND gates with a switch over here on the far right. So this switch determines which of the two inputs gets put on the output of each of our outputs. So again, we've got we've got 8 inputs or 2 sets of 4, and then we have 4 outputs. So this would allow you to, using this control over here, this switch, to tell which of the 4 inputs we want. If you take a look at the logical diagram, you can see it's just organized a little bit different. We've got all of our inputs, our 4 2 pair up here, and then we've got our outputs, and then we've got our switch on the right. Here's our truth table. It does have an enable pin, so just like some of the other chips that we saw, if we disable the input pin, it creates a high impedance input, therefore it won't drag down your serial bus, which again was super valuable when we had more kind of 8-bit computers that ran off of an internal bus. And then we've got the set select here, or the input select, and it only has 2 states, a high and a low. And then depending on whether it's high or low, it controls which of the inputs are being read in, the 4 on the left or the 4 on the right as the outputs. So let's go ahead and wire this up on the breadboard and see if we can make it work. I've got it wired up here on the breadboard, and I've got all the wires color coded, so it's a little bit easier to see. Now, I didn't notice this when I was looking at the data sheet, but the output is actually inverted. So if the pin is low, the output is high, as you'll see right here on this second row. So input low, output high, output low. So the way I have this wired up is I only have 2 switches, so this is only going to be controlling the first 2 of the inputs. And I have my enable pulled low, which is going to keep it on. And I have my switch also pulled low, which is going to be this first set here, the first lows. And we'll go ahead and rotate that around. Now, since each of them has 2 inputs, one of the inputs is tied to this switch, and then the other input is just tied. One is going to ground on these white wires, and the second one is going to 5 volts. And so they're reversed. But right now, those don't matter because my select switch is saying we want to use the L or the O's, or the first ones, so the first inputs. And so right now my switches will control it, as you can see, on and off, again inverted. And then here's my switch select. So if I move this from here to here, so now I'm saying I want that second set of switches. These switches now have no impact, and because I had one of them wired high and one of them wired low, or actually it's the other way around, one wired low and one wired high because it's inverted, you can see that's now what's on the output. And again, my input on my second input doesn't make any difference whatsoever. Now if I want to go back to that first input, I can just take this low again, and now my switches here work. And my second input, which is over here, which is ground, and if I just swap each of them around, you'll see it has no impact at all. And then when I put my switch back to the second position, you'll see my lights are now inverted. This one is off because the input is high, and this one's on because the input is low. So what might this be used for? Well, if you go back to the logical diagram, you'll notice that we've got 2 sets of 4 inputs, and we can control which one it's being read from. So if you think about a bus that might have 2 4-bit chunks of memory in it, and you wanted to be able to switch back and forth between them, you can have them both on the same bus, and then we can control which one gets read based on this switch right here. So the output is going to be on the bus. We can then set this switch in order to read from the first set of 4 or the second set of 4. And of course, we can do that super fast. And this chip would then handle that data direction as well. So anyway, that's kind of an interesting thing. Now this might be used as a control switch today. So if you think about, maybe you've got a multi-position switch and you need to know one of 4 positions, but then you also have a toggle switch up and down in order to set 2 different ranges. So for example, in one position, you'd be able to read the first 4, and then in the other range, you'd be able to read the second 4, all with that same control knob. So there's definitely some practical uses for it today. Again, we've got 8 inputs plus the switch, and then that produces just 4 outputs. So anyway, let's take a look at this on the oscilloscope and see how it performs. Got everything set up on the oscilloscope. I've got my chip here, and I'm only using the very first input. I've got my little circuit board here on the left. I've got this currently set at 976 hertz. and that's being fed in on the yellow line, and then the red line is going to be half of that, and that's going to be the switch, and that's going to switch it between the first and the second set, and then the yellow line is going to be my input, and then the blue line is going to be my output. And as you can see on the oscilloscope at this slow speed, it's keeping up just fine. Now keep in mind the output is inverted, so when it's high, or when it's low, it's going to be high on the output. And so anyway, just keep that in mind here as we go through it, because it's going to be inverted. So on the top here on my signal, when it's high, it's going to be low. When it's low, it's going to be high. Now I've got this cranked up to around 87 kilohertz, and as you can see, it's performing just fine, although the output is just a little bit lagging there when it goes low and then it goes high. I'm not sure why. Most of the other ones that we've seen have been very, very sharp. Let's crank this up a little bit and kind of see where it starts to fall apart. So here's 200 kilohertz, and here's 5 gigahertz. Let's zoom in. Yeah, that's kind of a mangled mess there. Not a whole lot of sharp edges on that. Let's crank it back just a little bit. And there's 1.4 megahertz. That's not too bad right there. That's probably pretty readable. So somewhere above 1.4 megahertz. Let's see if we can just move it up a little bit. 1.6, 1.7, 2 megahertz. 2 megahertz looks pretty good as well. 2.2, 2.6. Yeah, it's starting to get a little shaky there. Somewhere around 2, a little over 2 megahertz. It seems to be a little bit shaky. So yeah, so anyway, that's performing pretty well on that. Let me try a couple other things and see if we can do anything interesting. One final thing, and this isn't super interesting, but I was just kind of curious to see what would happen. I've got my 3 lines coming out of my pulse generator here. The yellow and the red are going into inputs 1 and 2, and then the green is switching between those two, and I don't have that one displayed on the oscilloscope. And then the blue is still the output. So the input is going to be either yellow or purple, and then the output is going to be based on this other switch. And if we pause that, you can kind of see how that looks on the oscilloscope. So you can see from the bottom purple here, or blue, that is clearly running pretty fast in order to get that type of a signal. But anyway, just not a whole lot of interesting things we can do on the oscilloscope with one of these. Again, this is a 2-input quad multiplexer switch. There's a lot of other potential practical uses for it, but just running it through on this here, it's behaving just as we would kind of expect it. There you go. There's a couple examples of some multiplexers. Not super interesting to look at. We did obviously get them both to work, and we put them both up on the oscilloscope and at least could see them function a little bit. You know, today a lot of this can be done very easily within a microcontroller, but back in the day, these were super important to be able to control the first round of computers. And this one here today, I still think there might be some practical use in it if you had a multi-stage switch that you wanted to be able to kind of control, and maybe you didn't have a lot of pins on your microcontroller to use. You could very easily use this because you could control essentially 8 different inputs with just 4 different inputs into your microcontroller. So definitely some slight advantage, although there might be easier chips to use. This one I thought was kind of interesting to look at it from analog signal standpoint. And this could be used in a digital switch if you had a couple audio signals coming in and you wanted to digitally be able to switch between them. You still could very easily use that. So anyway, I hope you enjoyed the video.